we will start our webinar. Welcome all on Data Phoenix webinar. Today we will speak about graph neural networks. Today with us Ekaterina Sirazitdinova. She is senior data scientist at NVIDIA. She will do introduction to graph neural networks. You can ask questions on Slander. The link is under the video. Also, you can join us on Zoom, where you can ask live questions, and we can have, I hope, good discussion. Also, don't forget to subscribe to our YouTube channel to know and participate in our next webinars. For now, I welcome Ekaterina. Your microphone.
Thank you, Dmitry, very much for having me today, and I'm super pleased to be here and present the introduction to graph neural networks to you. So, without further ado, let me share my screen and start the lecture. So you all should be able to see the slide now.
Yeah.
And perfect. All right, so the topic of my today's lecture is Introduction to Graph Neural Networks. And I work at NVIDIA as a data scientist for computer vision and deep learning. And you may wonder, why is she presenting graph neural networks? And the answer would be, I got curious about this topic and decided to learn it myself. And learning, I've decided, okay, I can actually share my learnings with some fellow colleagues. And by doing that, I've developed this lecture, which became kind of popular, and I gave it already a number of times. And I hope you'll also find it useful. So when I was giving this lecture before, the title was actually structured data. And the reason why I've changed it is that many people were confused knowing the notion of structured data from tabular data and databases. So that's why I've decided to change it to data with regular structure. And the thing is, there's so much data in this world which is structured or has a regular structure. Like, for example, in 1D, we have signal, speech, or text data. In 2D, we have images, which represent a structured matrix, the data structure. And in 3D, we have volumes, which can be cubes. If you're familiar with deep learning, you know that convolutional neural networks are very good in handling this data with regular structure. However, in this world, there is so much data which is not structured or doesn't have a regular structure. So here are a couple of examples of data with irregular structure. We can have volumetric meshes or surface meshes, for example, and all these are represented through, different nodes and different edges. Number of connections between elements in this data structures might be different. So this data has irregular structure. Another example of data with irregular structure would be knowledge graphs, where you have some different entities, and they can be also connected by different sorts of relationships between them. And also, you all know social networks and recommender systems. It is another example of data with irregular structure. So there we can have different devices, different applications running on different operation systems, having users, having connections between these users. So there's a huge mass of connections and entities in this data. To deal with this data, actually graph neural networks are very good at dealing with this kind of data. And in that sense, structured data like in tabular data, it's also very well suited for graph neural networks. One also good application of graph neural networks is in healthcare. So in healthcare, you can, for example, model graph as a graph. You can model connectomes in brain, like in MRI or DTI. Graphs are used in chemistry and pharmacy. So things like molecular analysis, drug discovery, and drug repurposing, they all rely on graph neural networks. In financial, we also can use graph neural networks for stock market prediction. And in physics, we can model particle systems or thermodynamical processes through graph neural networks as well. You may also wonder, can we actually represent an image as a graph? So image as a structured data representation, but can we apply here graphs too? And the answer is yes. In essence, image is also can be represented as a graph where the nodes of the graph will be each pixels, and the neighborhood information, like the connections between these pixels, will be the edges in the graph. However, here I must say that it's not the most optimal to represent images as graphs, because such graphs will be large and well, we are still a bit limited in terms of computations when it comes to large data structures. So in essence, you can actually represent anything as a graph. And well, once you've learned about graphs, at least how it happened to me, you kind of start seeing the world through the prism of graphs and how to model anything with graphs. So let's before we start learning actually how a graph neural network training works, let's just revisit the theory behind graphs. So what are graphs? Consider these bright dots on the screen our nodes. They are also called sometimes vertices when we, for example, are talking about volumetric representation in meshes in 3D. And the connections between these entities or nodes we usually call edges. And edges can be directed or undirected. In this slide, I'm showing you an example of directed edges. So you see that there are arrows here from this node to this node, and these are two arrows. This is a bidirected edge. As I already explained, based on the edges, if they are directed or undirected, we can have different kinds of graphs. So Facebook is an example of an undirected graph, because all the relationships, well, friends on Facebook, they are mutually connected. So it's a bidirectional relationship, or we can also call it an undirected graph. Another example of a directed graph is a social network like Twitter, because in Twitter we can have different relationships which are directed. So we can have one person sending messages to another, and this will be a sender and receiver. You can follow one person without and another person will not necessarily follow you back. So following on Twitter is directed. The same principle is on LinkedIn. You can follow people. This is directed, but LinkedIn also interesting in the sense that it also offers you undirected connections. Like you can connect with people and then it won't have any direction. There is another important notion of degree in a graph. So degree means usually a number of nodes, a number of other nodes connected to a current node in the graph. And in a directed graph, we have the notion of in degree and out degree. In degree means how many incoming edges a node has, and out degree how many outcoming edges. Graphs can be also homogeneous and heterogeneous, and a social network is a homogeneous graph because all the entities or nodes are of a homogeneous structure. So on a social network like Facebook, we have users and they are all the same. In e-commerce platform is an example of a heterogeneous graph. We can have users, we can have goods, and there are different ways of interaction between these entities. So users can either view products on the website, they can buy them, they can add them to wish list. So all these relationships are, well, different, and they're heterogeneous relationships. There's also another important notion of neighborhood when we are talking about graph neural networks. A neighborhood on a graph is basically all the adjacent neighbors from the current neighbors. So in this example, we have the node A, and those in yellow are its neighbors. And in this case, it will be the so-called one-hop neighborhood, meaning that all the neighbors are directly connected to this A node. There is also a notion of, well, two-hop neighborhood. These are the neighbors of the neighbors, and it can go even deeper and deeper up to the K neighborhood. When talking about graphs and graph learning, of course, it's also necessary to talk about graph representation. So how do we represent graphs in the computer memory so that we are able to work with them and learn on them? And one good representation of graphs is matrix. There are matrix representations of different kinds. And the first matrix kind is the so-called adjacency matrix. So in adjacency matrix, we encode, well, as I'm showing you here, we have a matrix of nodes. So A, B, C, D, E, F, in this case, are our nodes. And if we have a connection between, for example, a node A and B, we put 1 in our matrix. And if there is no connection, like, for example, in the case of A and C, so you see here, we put a 0 in this matrix. And for undirected graphs, you can see that this matrix is symmetrical, reflected relatively to the diagonal. If we are talking about weighted graphs, we can also represent it in the adjacency matrix. But instead of putting value of 1 integer value, we just multiply it to the weights of the edges between the pair of nodes. There's also another representation of a matrix, which is called degree matrix. And in degree matrix, we basically show the count of how many edges are connected to each node. So you see that we fill in these values in the diagonal. So for example, the node A has 2 connected edges, the node B has also 2 connected edges, and the node D will have 3 connected edges in this case. There's also the so-called Laplacian matrix representation, and this basically shows you how smooth the graph is. And the way to compute this matrix is basically we subtract from the diagonal matrix the adjacency matrix, and this is the so-called Laplacian matrix. Well, all these matrix representations, they are good if you're talking about some small graphs like molecules or some fixed graphs. However, this data structure has some shortcoming. First of all, it's not permutationally invariant, meaning that if you change the order of nodes in the matrix, you will get a completely different matrix, and it's not very good. And also another problem, if you have a very big sparse matrix, it will have just a few of entries and all will be zeros. So it will take lots of space, it will be huge, and also not, it will be not very computationally efficient to work with this data structure. In order to solve this problem, there is a different data structure, which is called adjacency list. And basically in adjacency list, you store the edge information as an adjacency vector of pairs between, which represent edges. So for example, if we have here A and B, we store this in our adjacency matrix. And this adjacency list can also have an accompanying lists of nodes and edges, which you can also store the numerical values if they are weighted, for example. With that, we are ready also to learn how deep learning on graphs works. But before we also touch learning on graphs, let's just revisit how deep learning works in general. So in the essence of deep learning is that we have an untrained neural network, and our goal is to learn some certain capabilities from data and store them in the network in order to give this network predictive powers to work on unseen data. So to train a neural network, what we need is a data set, a training data set. And the states through which this network is coming, training state, means that going through this data set and extracting some certain specific patterns and storing them within this network in the form of the so-called weights. So by showing multiple examples and extracting this specific patterns, we have a neural network with the newly learned capability to recognize recognize data. And the next state of a neural network is called inference. And by inference, we understand applying this capability, this learned capability, to the new unseen data. So if, for example, we have trained a neural network by showing it thousands of cat images, we got a network which is able to recognize cats. And now if we show an image of an unseen cat, the network will be still able to predict there is a cat in this image. Another important notion to mention is the notion of supervised and unsupervised learning. So when we're talking about supervised learning, we mean that we have a data set and we have labels in the data set. Usually we need an expert, or yourself as an engineer. You can also be an expert if there is something simple, like for example, apples or bananas. You show your network thousands of these images and labels, and network says, okay, it kind of like, it maps the images to the labels. And the unsupervised learning is basically you bring your unlabeled data set and the network tries to figure it out on its own, whether they're apples or bananas or some other structures. And there is another notion of the so-called semi-supervised learning. And in semi-supervised learning, you typically label a fraction of your data set, and the rest of the network also learns from this fraction. And many graph neural networks are designed to be semi-supervised learning networks. So let's see what kinds of graph neural networks we can have and what tasks do they solve. And let's come back to our graph. And we've learned that we have nodes and edges. And in addition to, well, the basic structure, all nodes in the graph can have the so-called features. The edges can also have features, and we can also have global graph features. So on all these three levels, we can have different features. And by features, we understand some distinctive characteristics. And basically, our task when we talk about graph neural networks is to take this input with nodes, the structure between them, and the specific features, and learn some specific function or graph neural network in order to get the output. And we can have outputs of 3 different types. We can either predict new node features, new edge features, or new global graph features. Let's go through them one by one. And the first output type are new global graph features. So when comparing it to traditional convolutional neural networks, it would be like classifying your graph. Let's see some examples of this. Well, the classification, a good example of a classification is this paper I found by Google. They've run this very interesting experiment to predict the smell of molecules by framing all molecules as graphs. So by doing that, they were able to predict smells of new molecules which are not labeled in the data set. Very, very interesting use case. Also, graph level tasks can be viewed as a regression problem. And here, another good example is a discovery done by MIT. They have discovered an antibiotic called halicin, which is basically a new antibiotic effective against some multi-resistant bacteria. And they were able to predict ratings of molecule toxicity. And for those of you who are not familiar with regression and regression versus classification, well, in classification, we predict some discrete values. In regression, we predict some numerical or continuous value. It could be like a person's height or weight, weather, and things like that. So in this case, the value of toxicity was predicted by graph neural network. When we have the output as a new node feature, so this means that we are predicting this features on every node. So let's say they are unknown from the beginning and we want to learn based on what we have, the values of these features. And yeah, if you compare it to convolutional neural networks in image processing, this might be compared to segmentation. If you know, in segmentation, our goal is to label each individual pixel in the image, for example, saying that it belongs to class A or B, and we can do it on graphs as well. And one good example of that applied to graphs would be the so-called Zachary Karate Club, which is also considered to be the hello world of GNNs. And the idea behind is that by using the university neural network to predict the following. So in one small town, there is a karate club. And there is an instructor and the administrator of this club who got into fights, and big conflict arose between those two. And basically, based on that, the club split into parts. The first part went with the instructor, and the second part, they just dropped karate or found some other trainers. And the task here is to, using the university social network, is to predict who of the students, based on their connections, remained in the karate club with the instructor and who has dropped karate. There are many of examples on GitHub. The data set is available, so I highly encourage you to look it up and try it out. On the regression task, we can also have node level prediction. So a good example here, which I found from NeurIPS of 2021, to predict values of crop yield in different states and different spatial geographies of the United States. So the researchers of Cornell did this work utilizing geospatial and temporal information to do that. So very, very useful application. Another task based on the output is to predict new edge features. And by edge features, we understand this colors in green. So let's see what kind of edge prediction tasks we can have. So the first example is a link prediction. And you all may know this feature of social networks where we can, well, recommend a new friend, or a feature of e-commerce to recommend a product to buy. So this is done by link prediction. And another type of edge level task is a classification. So one good example is predicting fraudulent transactions in a bank system. So we have, for example, credit card holders and merchants, and the transactions, the value of transaction between them could be the value of edge. And we can say if the transaction was fraudulent or not based on this graph information. This example I really like, the regression on edge level. And I found it in a white paper published by DeepMind, where they explain how they perform the estimation of time travel from A to B. And the way they do it, they take the whole route and they subdivide it into chunks. And each chunk is basically a node in a graph. And then they estimate the values of edges between these graphs. And by combining them together, they get a complete ETA estimation. So to the most important part, how do we do the GNN training? And the intuition of GNN is actually that nodes are naturally defined by their neighbors and connections. Let's try to understand this. So we can simply imagine that if we remove the neighbors and connections around the node, then the node will lose all its information. And therefore, the neighbors of a node and connections of neighbors, they will define the concept of the node. And having that in mind, we then give every node some certain state, let's call it X, to represent this concept. And when then we can use the node's state to produce so-called output, or the decision about that concept. And then the final state, Xn, of the node is normally called node embedding. Those of you who are familiar with natural language processing, you may have heard already the notion of embedding. So this is applied to graph neural networks. This is very similar, has the same meaning. And the task of a GNN is to determine the node embedding of each node by looking at the information on its neighborhood nodes. So let's see how it works. The intuition of spatial GNNs is very similar to convolutional neural network. So in short, the idea of convolution on an image is to sum the neighboring pixels around the central pixel, specified by a filter with some parameterized size and learnable weight. But we can also perform it on irregular domain, and spatial convolutional neural network adopts the same idea by aggregating the features of neighboring nodes into the center node. So the core of spatial GCNs is the neighborhood aggregation scheme, which generates the node embeddings by combining information from the neighborhoods. So let's see how it works. And on this slide, I'm showing you an input graph. This is just a random graph I've created for the convenience. So on this graph, we have nodes A, B, C, D, and F, and they're connected. The connections are not directed. And let's say we are now in the current node C. What's great about this approach is that it is permutationally invariant, and it doesn't matter where we start. So we can start at some randomly chosen node C in that case. And now what we are going to do, we are going to show how message passing works. So we have the node C, and we have the nodes B and D, which are its neighbors. So node C is here. What we do now, we take the information for node B and node D, and we aggregate them together and pass through some other neural network or some layer. And then we also add this information to the node C. And then we do again, the same again with the neighbors of the node B and the neighbors of the node D. And you can do it up to the K neighborhood. What's even more, in addition to this neural network, we can also place a neural network or something like multi-layer perceptron or recurrent neural network in each node as well. So it's becoming a little bit complex, but by doing that, you can encode a lot of information. And by repeating this step n times for all nodes in the graph, the feature representations are updated with information of nodes up to n hops away. And as an engineer here, your goal is actually to find this n. So it's basically your hyperparameter. You try to choose in order to see what fits the best for your task at hand. So we can stack a number of these GNN layers. So let's say we have a layer K. The current node is still C. And we take the features from the neighboring nodes, we aggregate them, and we transform them to get the new representation, the layer K+1. So we have collected, aggregated, and transformed this information, and now it became the new version, and the values have changed as well. In addition to that, well, this is how the message passing works. In addition to that, and which is a little bit out of scope of this lecture, there is a number of different architectures how to do that. So we have popular GNN architectures like the message passing I've described, and it uses message passing to propagate the information between the nodes in the graphs. Then there is a graph sage, and graph sage is basically a generalization of graph convolutional networks that aggregates the features of a node's neighbors to generate node representation. There is a popular graph attention networks, and they use the so-called self-attention mechanism to weigh the importance of each neighbor node when computing the representation of a particular node. We also have graph neural networks with edge embeddings, and it's a special type of GNNs that incorporates edge embedding to capture more information about the graph structure. And then there are also the so-called spectral graph convolutional neural networks. These spectral graph convolutional neural networks, the key idea behind is to leverage the spectral properties of the graph Laplacian matrix, which encodes the graph structure to define convolutional features, filters that can operate on the graph. So these spectral graphs, they are also convolutional neural networks, but they are different ways to propagate the information in this type of networks. And these are just some examples. There are many, many more like ChebNets and other examples. So if you want to learn deeper, I highly encourage you to look up these networks and other networks as well. And the rest is quite easy. So there are the same concepts as in classical convolutional neural network training. We have also activations on the graphs. We perform normalization in graph. There is, of course, a loss function. If you're talking about, for example, the supervised learning, we compare the output and the ground truth, and then we perform the optimization step. And of course, we perform gradient descent and backpropagation. If you're new to deep learning, I really highly encourage you to also look up these definitions. Where to start? The good news here is that you don't have to implement this all from scratch, and there are good libraries and frameworks available. There is a PyTorch geometric, which is very popular, or if you're a TensorFlow person, they have also recently introduced their graph extension. There's also a popular framework called Deep Graph Library, which is basically a framework agnostic, and you can work either on TensorFlow or PyTorch with DGL. And they also have some really nice tutorials, some good examples of how to work with graphs. With NVIDIA, we also provide our own containers on NGC. NGC is the so-called NVIDIA GPU cloud, which is not a cloud, but a repository where we store our containerized software, free to use, and of course, optimized for our GPUs. We have also partnered with the DGL team, and we also have our release, which consists of 2 containers. I'm providing the information here, and you can find them by downloading them in the links. The QR code on the upper right corner leads to a nice presentation by my colleague, who is explaining you all about these containers and how you can use them. As a further literature, I can recommend you these references. So these are really nice articles and blog posts, which back in the day helped me to understand the concepts of graph neural networks. And I also highly encourage you to subscribe to our NVIDIA developer program, which is basically a community where you can talk to fellow developers, you can post on our forum, and if you have any questions to our software or our technologies, you can always ask there, and it's been monitored by my colleagues, engineers who, well, constantly answer there. And last but not least, if you have a startup, and if you want to also develop in AI and in the GPU space, we offer our Inception program. The participation in this Inception program is also free, and if you participate there, you get some certain benefits. With that, let me summarize the findings. Let me summarize my lecture. So here today, we've learned that you can actually model everything at a graph, and that there are different kinds and properties of graphs. We also learned that there are different graph representations, such as adjacency matrix or adjacency lists. And we've also learned that adjacency matrix, they are not permutationally invariant. And if we have a really big data structure and sparse data structure, then it's definitely preferred to use adjacency lists. We have learned different flavors of graph learning. So we have tasks where we want to do node level, graph level, and edge level predictions. And we've learned that the key way to learn with graphs is by using embeddings. We've got familiar with the message passing concept, which is the driving concept behind message passing graph neural networks. And we've learned that there are 3 major steps we need to perform, which are aggregate, transform, and update the value to learn your embeddings. And finally, I've shared with you that you don't need to implement everything from scratch, because there are already nice frameworks are available, like DGL, PyTorch Geometric, or TF-GNN. With that, thank you so much for joining, and I think we have some time for the Q&A.
Yeah, thank you for so good presentation and introduction for graph neural networks. Yeah, we have some questions. I will share the Slido board where we can select and answer the questions.
Shall I keep sharing my screen or no? Okay.
Yeah, so we have 8 questions.
Are there any neural networks similar to UNet, but based on graph neural network? It's an interesting question. So if you remember when I was talking about prediction on node levels, and I've compared it to segmentation. So UNet is a segmentation network, right? And applied to graph neural networks, you will basically think of it as predicting every pixel as a node level, right? So I'm not aware if graph neural networks used for segmentation, image segmentation tasks. I must say I didn't do this research because when we talk about images, it's still more efficient to use convolutional neural networks or transformer architectures. And that's why maybe there are architectures for that, but I'm not sure if it's the most efficient way. As I said, images are big, and representing it as a graph, as a dense graph, it might be not the most computationally efficient. Although I've already mentioned now transformers, and transformer is basically a kind of a graph representation as well. So if you think about that in this light, there are transformer architectures which are also used for image segmentations. So when having that in mind, we can actually say that, yes, you can consider transformers as a graph neural networks which do similar things as unit do. Check, for example, the popular segformer architecture.
Yeah.
Go into the next question. Do you have any comment, Dmitry?
No. You can continue.
Okay, so have you had any experience with tasks where you need to convert a regular structured input, volume 3D voxel data, into an irregular structured graph? Well, it's also from the similar field. And as I said, convolutional neural networks are good for working with structured data. And if you want the most efficiency, you just need to find the most efficient neural network representation. You can surely do that, but the question is, will it be very efficient or not? The next question is what you could recommend for temporal graphs. I'm not sure if I understand the question correctly, so what could I recommend? Is it possible to get any clarification?
No, we don't have any.
Oh, okay.
Maybe they will write additional question.
What data size is required for tasks using graphs compared to regular structures? Well, if I remember it correctly, you're asking about a data set size, and data sets we need to learn in deep learning, and graph neural network learning is a deep learning. We usually need big data sets, so you still need a lot of data. If you don't have a lot of data, then you're probably better off with a traditional machine learning. All right, the next one. Would Meta's new AI segment anything work in a similar way? And yeah, I saw many news about this segment anything today. It's well, I don't know what's the algorithm behind. I must admit I didn't have time to really read deep into the announcement. What I know is more similar to a large language model where you rely on prompting, but I cannot provide any one-to-one comparison to graph neural networks here. Any recommendation on how to build or represent your graph in order to train a model with good accuracy? Well, in order to train a model with good accuracy, you need to experiment with many things. So first of all, well, you definitely need to build your graph in a specific way. There are hyperparameters controlling accuracy. There is a data set. So there are multiple factors affecting this. So it's not only the architecture which decides here. And depending on the task you have, you might look into different graph architectures, but there is no one-fits-all solution. Next question. What do you recommend to convert data collected from IoT networks to graph structured data? That's a good one. So yes, you can do that because the data collected from IoT networks is in a sense unstructured. Of course, we can have structured data like data collected from video, but we can also have some other sensory information like temperature, all other things. And yes, graph representation is a good use case for IoT network data. The question about unit was not only about the segmentation, but also about the presence of a bottleneck, but for mesh for graph base. I mean, okay, I understand. Yeah, theoretically, it should be possible. I'm not aware of any architectures like that, but maybe possible. Maybe you're the first person who would experiment with that. I don't know. Can you brief about dynamic graph training? Here I must say I'm not an expert. That's why I cannot comment on that. What tools are the best for high load inference to be in milliseconds for 1K records? So I would take it as a question of inference optimization in general. And the best tool I can recommend you is our NVIDIA TensorRT, which is an optimizing compiler, which performs a set of optimization techniques in order to get the most out of your inference. Can we use GNN to predict edges dynamically, taking into account both the present condition of the graph as well as the historical data? The only thing I can tell you is yes, there are approaches which are dealing with that. Thanks for the presentation. Did I understand correctly that NLP attention mechanism is somewhat similar to representing information as a graph? Yes, it is very similar. Are there approaches to learn the connectivity of the graph as well? By that you mean is it directional or indirectional, or is there connections between nodes? In both cases, actually, yes. So the example I've shown you is link prediction. Like, for example, when we suggest friends on Facebook or goods to buy, this is the link prediction example. And this is the same. Well, what are you asking? The next one, what about large graphs with millions of billions of nodes? You reach these numbers easily in fraud detection. Are GNNs feasible computation-wise? Yes, GNNs are good applications for this. Of course, there are ways to work with large graphs. And on the slide where I mentioned the DGL container by NVIDIA, and my colleague Kyle, he has a good lecture about working with large graphs. So there was a QR code, yeah.
Yeah, so it was last questions. Yeah, so thank you for this presentation. Again, thank you for all that was with us. See you on the next webinars.
Thank you for having me.